Pressure surge is not an outlier. Your anomaly detector flags a pressure spike. It pages an engineer. The engineer looks at it, rolls their eyes, maybe sucks their teeth aggressively, and then goes back to bed. Why? Because compressor discharge pressure surges on load changes. That is not an anomaly. That's a valve transition, and that's a normal Tuesday. But if your training data was smooth, if your synthetic data did not include transients, your model never learned the difference. Today, I'll show you how to put real pressure surges into simulated data. Okay? All right, let's look at the config. This is our discharge pressure PSIG generator. It uses a random walk starting at 1200 PSIG. And that is a realistic pressure for a pipeline booster station with suction around 450 PSIG and discharge around 1200. But the interesting parameters are shock bias, shock rate, and shock magnitude. First, let's look at shock rate. Here we set it to 3%, and that means that we have a 3% chance of a transient event in any given time step. So with over 288 5-minute readings per day, that's roughly 8 or 9 events. It's a bit aggressive, but you get plenty of data for your model. The shock magnitude we set to 50, and that means that each spike that we see can go up to 50 psi above the current value. So if you'll see discharge pressure jump from 1200 to 1250 and then come back down. The shock bias is a directional flag. A value of 1 means that the shock always goes up and never down, and that is physically correct. You never see pressure, shock downwards. And if you set it to 0, then you get random direction. And set it to -1, then it always goes down. But for compressor surges, 1 is what the physics says. All right, let's run the simulation. Down. Okay, so as you can see, our baseline is around 1200 PSIG, and that's exactly where we set it in the YAML. The random walk keeps it wandering between 1100 and 1400, and the mean reversion tries to pull it back to 1200. Now you see two kinds of specs here. The first one is our actual shock that we set, which, like I said, spikes from our baseline of 1200 and goes up to 1250, then comes back down. And that's always going upwards, and those are real process transient. And they look like they're part of the signal because they are. But then you see these massive spikes that go all the way up to 3000 PSIG. Those are not process events, and those are part of the chaos system, which we covered in previous videos. We go up back to the YAML. Let's actually open the YAML and look for our chaos, right? We set it to 0.008 with an outlier factor of 0.2. That's simulating sensor glitches and the pressure transmitter getting an electrical spike. And suddenly it reads 2.5 times its actual value, which is why we see roughly 3000 PSIG. And that just looks like garbage data. We need both types of data in our models so that we get a full range of what we see in reality. Back. Okay, so we have two different phenomenons. We have two different configs, and your anomaly detector needs to handle them differently. The shock events that we see here at 3% are normal operations, and flagging those and paging your engineers for nothing is not fun. The chaos that we see are actual data quality issues. Those we want to catch and we want to quarantine. That's the difference between a transient and an outlier. One is physics, The other is broken center. Okay. And here we see our distribution. And I will share the link to this notebook at a future date. But in closing, we have two systems working together. We have the shock parameter, which includes, or shock parameters, which includes the shock rate, the shock magnitude, and the shock bias. And that gives you realistic process transients that stays within physical bounds. The chaos parameters, which is the outlier rate and the outlier factor, gives you sensor glitches that blow past those bounds that we set. Your anomaly needs to learn the difference, and it can only learn that difference if your training data includes them both. Thank you.